Okay, so in this section, section 1.3, we're going to talk about the two main ways that we collect data, which is through experiments and observational studies. And we're going to talk about the types of inferences that we can make when we use each of these different types of studies. And so, of course, we're going to start with some more definitions. If one definition is fun and two is funner, then 500 is even funner than that. Okay, so first definition is going to be association. Okay, so association, when two variables are associated, it means that values of one variable tend to be related to values of the other variable. So two variables are associated when values of one variable tend to be related to values of the other variable. Okay, so one example would be temperature outside, the average temperature outside, and electric bill. So I'll say average, high temp, and electric bill. If I can spell bill. Okay, so association just means that values of one variable tend to be related to values of the other variable. So if we're talking about the average high temperature for the month and electric bill, when the average high temperature is higher, then my electric bill is also higher. And then when the average high temperature is lower, my electric bill is lower. So high values of the first variable are associated with high values of the other variable. And especially right now in the heat of summer. Okay, somebody asked, is this the same as correlation? And yes, yeah, if two variables are associated, we also say that they have a correlation. So we kind of don't use that term in our class until chapter 2. But yes, if you've talked about correlation in other classes, like association is just like correlation, exactly. All right, so our next term here is causation. Okay, and two variables are causally associated if changing the value of one variable influences values of the other variable. So two variables are causally associated if changing the value of one variable influences values of the other variable. Okay, so in the case of the temperature and the electric bill, if I were somehow able to manipulate the average temperature outside, so let's say for September, instead of always having it be so hot, even though you're ready for summer to be over and you can't believe it's this hot, even though you've lived in Texas for 20 years. Let's say I was somehow able to say, okay, for September, I'm gonna make the average temperature, I know this is impossible, but if I could make the average temperature 65 instead of whatever it is, super hot, would that cause my electric bill to be different? Would it cause it to go down? So if I could change the temperature, would that cause my electric bill to change? Is the temperature what is causing my electric bill to be high? Yeah, so in the case of the temperature and the electric bill, there is a causal association there. The high temperatures outside are causing my electric bill to be high because air conditioner is running all the time. I have, 5 million kids, they're running in and out all the time. So our electric bill during the hot months is astronomical. So in fact, if I told you what it was, it would make you all feel better about your own electric bills probably. Okay, further up, I just saw something. Okay, so correlation is one of two types of association. Causation is the other. So correlation, and this is what we're going to talk about next, is a correlation and association are not the same as causation. Okay, so just because we have a correlation or we have an association does not necessarily mean that it's a causal association. So we have to be very careful with using the word cause. So I'll write that down here. So association is not causation. Whoops, I don't know why I jumped up there. All right, and this is like a super important point that I want you guys to understand this semester. This is probably one of the bigger concepts that I want you to learn this semester, which is why I'm putting stars all over it. Is this idea that association is not causation, because frequently you're going to read on the internet, hear in the news, all over, people that are trying to imply a cause and effect relationship when maybe the way that they collected their data does not support that they can make that conclusion. It happens all the time. So I want you guys to be very careful when you hear the word cause, and I want you to ask, how was this data collected? And based on how it was collected, can we draw a cause and effect conclusion? All right, so little example here of how this could go awry. Okay, let's say that I looked at ice cream sales versus drownings. Okay, so if I looked at ice cream sales and drownings and did like a little scatter plot here, I'll see if I can write ice cream. Okay, so let's say there's ice cream down there and this is drownings. I don't actually have my computer pen plugged in, so this is just my mouse and I'm doing a terrible job, but you know what it says. Okay, so if I looked at ice cream sales and drownings, it turns out that there actually is, I mean, I know I just put this graph up here, but if you looked at the real data, there actually is an association between ice cream sales and drownings. So higher ice cream sales is associated with higher drownings. So does that mean that ice cream causes drownings? Like, you know, your mom said, wait 30 minutes after you have ice cream to go swimming, but you didn't listen to your mom, you went swimming anyway, so we have more drownings? Or does it mean that maybe drownings cause ice cream? Like your best friend drowns, you're depressed, you go buy a pint of Ben & Jerry's, make you feel better? Okay, no, right? Ice cream doesn't cause drownings. Drownings don't cause ice cream sales. So why would we see this positive association between ice cream sales and drownings? Oh, good. So I see in the comment window somebody said summer. Yeah, the temperature outside is basically this outside variable that's actually driving that association between ice cream sales and drowning. So exactly, Brianna says people like ice cream when it's hot. Absolutely. And more people go swimming when it's hot. So you're going to end up with more drownings overall. And then in the cooler months, then people are less excited about eating ice cream. They probably, I don't know, want to go to Starbucks or something instead. And they're less people are going swimming, so we get fewer drownings. So even though we see this association here, it doesn't mean that one variable causes the other, okay? And we're going to find out that the only way that we can show a cause and effect relationship is by doing an experiment. So let's see. Okay, so let me write down one more definition here on this page before we end. I guess I'll just write it on top of this. I don't know, maybe I can sort of clear some things. I'll just make this bigger, then I can just write it in here. There we go. Okay. So Clarissa says, is the weather the explanatory variable? So we don't call it the explanatory variable because it's not even showing up in our graph here, just ice cream and drownings are. Instead, we call it a confounding variable, which is like this, essentially this other variable, a third variable that's not even on our graph, that's actually driving that relationship. So it's called a confounding variable, or sometimes I call it a lurking variable. And a confounding variable or lurking variable is a third variable that is associated with both the explanatory and response. So it's a third variable that is associated with both the explanatory and response variables, and can offer a plausible explanation for the association. and can offer a plausible explanation for the association. Can you guys see that? Sorry, it's kind of messy because maybe if I make this part, no, I can't make it bigger. Make that go over there. It probably just looks like a mess. Maybe if I made a different color, maybe I'm worrying too much about it. I'll turn it green. Okay, so write down that definition. All right, so here's another example of a time when we're going to have a confounding variable. So if we look at the number of TVs per 1,000 people and we look at life expectancy, then again, we're going to see a positive relationship. So does that mean that we can just, you know, solve all the world problems by getting everybody a TV? Like Netflix saves lives, hooray? No. Okay, if we look at these countries up here, we can see that these ones that have high values, so lots of TVs per 1,000 people and a higher life expectancy, it's France, Canada, United Kingdom, United States. Okay, and if we look at these lower values down here, so not as many TVs and lower life expectancy, we've got Cambodia, Madagascar, Haiti, Uganda. So what's probably the confounding variable that is actually the explanation for this association? Yeah, exactly. Like wealth or poverty, right? We've got all these like third world countries down here at the bottom that don't have resources. They don't have, the people probably don't have as much money to buy TVs. They don't have money to access healthcare. Whereas up at the top here, you know, we've got all the wealthier countries that have all of those things. So definitely. All right, so we're gonna write down a couple more terms here. So we talked about how there's two methods for collecting data. We mentioned these at the beginning. Now we're going to talk a little bit more about what those two things are. Okay, so there are two methods for collecting data. The first method is an observational study. Okay, in an observational study, then we're going to observe individuals, measure characteristics of interest, but we do not actively control the value of any variable. So we're going to observe individuals, measure characteristics of interest. Oops. So we're going to observe individuals, measure characteristics of interest, but do not actively control the value of any variable. Okay, so a lot of surveys are observational studies because we're just asking people things. We're asking for their preferences or things about them. We're not actually controlling the levels of any of those variables. We could also do an observational study where we actually just sit down and observe. So we watch people or things like that. Okay, then we have our other method for data collection, which is an experiment. Okay, in an experiment, then the researcher actively controls one or more of the explanatory variables. Okay, so in an experiment, then the researcher is controlling the levels of one of the variables. So let's say that we want to do a study on pain medication, and then we're going to find some people who are willing to let us cause them pain. Like if you've ever seen any of those advertisements where they're like, hey, we'll take your wisdom teeth out for free. Really what they're saying is, hey, we're doing a study on pain medication and we want to be able to cause you lots of pain so we can see which pain medication works the best. So in that case, then the researchers would use a random number generator, of course, to randomly select which pain medication that you are going to get. And you probably won't know which one you're getting, and they'll, you know, have you sit there, and every half hour or so they'll come say, how much pain are you in? And by that way they can compare the different pain medications. But the researchers are controlling which pain medication you get. Now, in order to draw a cause and effect conclusion, you have to do a randomized experiment. And it's a randomized experiment if the value of the explanatory variable is determined randomly. So that's the good kind of experiment. So cause and effect conclusions can only be drawn from randomized experiments. Okay, so if you have an observational study, you can't draw a cause and effect conclusion. It's really, yeah, you just can't draw a cause and effect conclusion from an observational study because you're going to have so much confounding going on. Whereas in an experiment, because we're controlling the values of the variables, then we're going to eliminate that confounding variable. Okay, I'm going to talk about two different types of randomized experiments. These are the two types. Obviously, just like with sampling, there's lots of different sample designs. There's also lots of different experimental designs. In fact, like both of those things, like I took I actually took two classes, whole classes in college on sampling design, and I did take two classes in college on experimental design. So, I mean, there are so many different designs out there, but in our class, we're going to focus on just a couple. So I'm going to delete this top part so I can start writing the bottom part down here without, hopefully you've gotten the other part written. So we're going to talk about types of randomized experiments. Okay, and these are the two types that I'm going to expect you to know about in our class. So one is a randomized comparative experiment. Okay, in a randomized comparative experiment, all the subjects are allocated among all the treatments at random. So all subjects are assigned at random to all the treatments. Okay, so we basically just take everybody we have and then, you know, we just randomly assign them to all the different treatments that we have. So depending on how many treatments you have, like as long as you're using a random method like a computer generator, you could also flip a coin. If there's only two treatments that you had, you could roll a dice. So any truly random method to assign people to the treatments is great. But you're just taking everybody, randomly assigning everybody. The other one is called a matched pairs design. Okay, in a matched pairs design, then we're going to first pair up your subjects so that they're as alike as possible. So first you're going to pair up your subjects so they're as alike as possible, and then you're going to randomly assign the treatment within the pair. Okay, and the reason for doing a matched pairs design is just that you're going to be able to get rid of some other factors that might be influencing the results that you kind of don't really care about. So for example, if I was comparing two diet plans and I'm measuring weight loss, well, there's other things that can affect weight loss besides just the diet you're on, like, you know, your genetics, your gender, how overweight you are to begin with, your activity level. So all those things are going to affect your weight loss in addition to the diet. So if we take people and we pair them up so that they're very similar in all those other characteristics, so that the main thing that's different between the two people is the diet that they're on, then our end results are going to be more distinct. We're going to be able to tell the difference. We can also use a single person and give them both treatments, but in a random order, and that way a person can be the pair. So a single subject, let me just reword that. I'm going to say a pair can also be one individual who receives both treatments. So taste test, they do some drug studies this way where they kind of have a washout period in between, are done as matched pair studies. So these are the two that we're going to learn how to analyze here in our class. All right, so at the end of the day, when we're looking at a study and we want to be able to determine, okay, what kind of conclusions can we draw from that study? It's going to come down to asking 2 questions. Okay, so here's the 2 questions that we have to ask of any study. Okay, we want to ask, was the sample randomly selected? Okay, so did we take a simple random sample from the population or something like that to select our sample? So if we did, then it is going to be possible to generalize to the whole population. If the answer is no, then we cannot generalize the results to the whole population. Okay, the second question that we're going to ask is, was the explanatory variable randomly assigned? And by asking this, we're essentially asking, did we do a randomized experiment? That's another way of asking this question here. So if the explanatory variable is randomly assigned, then it is going to be possible to make conclusions about causality. If it's not randomly assigned, then we cannot make cause and effect conclusions. Okay, so write down those 2 questions and the type of write down the stuff on this slide. I know I didn't write it myself, but this is important. So if you can write it down, I would write it down. Okay, I mean, of course, ideally, it would be awesome if we could take a random sample and then do an experiment on our random sample every time. But the reality is that it's often impossible or even unethical to take a random sample for things like let's say we're doing a pain study. We can't just like look at all the people in the US and randomly select people and say, hey, guess what? You were randomly selected for me to cause you a lot of pain. So instead we have to get a volunteer if we're going to do that. So if our end goal is to generalize to the population, we want to make sure we get a random sample. And if our end goal is to show a cause and effect relationship, then we want to make sure that we're doing an experiment. So that's kind of the gist of it, and the 2 types of inference that we can draw based on that. All right, we're totally out of time. Hang on, there's a question in the chat window. Is there a minimum sample size in order to be able to generalize the results to the population? That is a really good question, and the answer is no. There is not a minimum sample size. And we're going to see in our class that actually a lot of times you can have a fairly small sample size with relation to the population that can do a pretty good job. We are going to learn in future chapters like what kind of conclusions you can draw with smaller sample size versus larger sample size, and how that affects like we're going to talk about confidence intervals and how that's going to affect like the width of our confidence interval. But if you're using a random method to select your sample from the population, then you can make valid conclusions about the population based on your sample data. So good question.